Okay, so today we're going to talk about equilibrium, which is the state at which two opposing forces or influences are balanced. And we're going to eventually talk about chemical equilibrium, but this is a concept that has implications in biology, in ecosystems, in economics. So it's really one of the fundamental concepts that help rule the world we live in. So I'm going to give you an example here, and then we're going to talk about chemistry, specifically the Chatelier's principle, and then maybe relate that to things that are going on in the world today. So what we have here are two graduated cylinders, one skinnier than the other, and here we have a stopper that prevents water from moving back and forth. So if we look at this situation, we have a lot more water in the skinny cylinder as opposed to the thicker one, even though there's probably just as much water flowing in both of the cylinders because this one is thicker, it contains more water than the thinner one does. In this situation, we have the opposite. There's a lot more water going on over here than there is over here. But if we were to turn this stopper the other way and allow water to flow between the two cylinders, what we would see is water would reach the same level in both cylinders. Now it doesn't mean that there's the same amount of water in both cylinders. As you can see, there's 60 mils in this one and 30 mils in the skinnier one. But the forces that control this system, which would be buoyancy and water hydroelectric forces, which are primarily determined by the height of the water, those come to equilibrium, and we see that the height of the water is the same, despite there being different amounts of water in both sides of the cylinder. So that's a simple way of, a simple reaction where equilibrium takes place. Now we're going to move on to chemical equilibrium, where we normally talk about concentrations or partial pressures of products, which are just fancy ways of saying how much do we have. So the way I like to explain Le Chatelier's principle, which states that the equilibrium will shift in order to relieve the stress. Let's say we have this process, the Haber process, where ammonia decomposes to give us nitrogen gas and hydrogen gas. Let's say we have this system, right? Let's say we have it in a cylinder, right, where we cover it up, so there's the same amount of ammonia gas that's decomposing into nitrogen, and hydrogen is the same amount of hydrogen and nitrogen forming to form ammonia. Let's say that we open the cylinder up and allow nitrogen gas to flow through, but hydrogen gas would not flow through. The way I like to represent this is to draw nitrogen really small. It's much smaller in terms of the size than it is than the other two. And what this represents is sort of a scale, right? There's a scale where the original, it was completely balanced, right? If you saw someone on a seesaw and someone that was my size and weight on a seesaw, we would both be balancing. If you put someone else on the other side of that seesaw, I would immediately rise to the top. It's the same idea here, except in this case it's chemical concentrations, or the amounts of reactants and products. So if we were to draw nitrogen like this, meaning the concentration went down, what would happen in this reaction? Well, since if we look at this like a scale, this thing has to come to balance, right? That balance beam has to eventually reach an equilibrium. We have to make more of this. That's the only way we can balance this. So what ends up happening is this goes down. The amount of ammonia gas, more ammonia gas decomposes to fill nitrogen gas and hydrogen gas. So if this goes down, we're going to raise this up to its somewhat original level, not exactly, but enough to balance the two sides of the equation. And then this is going to go up. Okay, so we have more ammonia decomposing to counteract the fact that we have a small amount of nitrogen, and as a result we have more hydrogen gas than we started with. And if we were to represent this as an equation, what we would say is the chemical equilibrium constant, this is an equilibrium constant, would equal the amount of products, which are nitrogen and hydrogen, over the reactants, which would be ammonia gas. And if we would decrease nitrogen and increase hydrogen, and then decrease ammonia, this number would always be the same. So finally, we have this reaction. And I just want you to think about this for a second. We'll probably delve into this a little deeper later, that what would happen if in this reaction where carbon dioxide reacts with carbonate and water to form calcium ions and carbonate ions, what would happen if we were to increase the amount of carbon dioxide to the system? So in the same way we handled the Haber process, where we decrease nitrogen and then as a result balance this equation, think about what would happen if we were to increase the concentration of carbon dioxide in this process. Thanks.